Okay. Okay. So I've gotten feedback from the vast majority of you guys. So remember, test corrections are due by Friday. So please get those back. Several people have already turned them in. I appreciate that. It will likely be after the weekend before Sakshi and I can get sort of through all of those and get your grades updated from there, get your bonus points from doing the course evaluation added in. So don't freak out if like you turn it in today and your grade doesn't immediately change today. Okay, it'll take us a little bit, but we'll get it fixed up for you guys by next week. Okay, so I want to let you guys know what we're going to try a couple of things a little bit different based upon some of the feedback that I got, which I appreciate very much. I may put a compilation together of some of the things that were said to illustrate that many of you will say one thing and then the next person says the exact opposite. And it's really fascinating to me in some ways. People are like, nope, love the PowerPoint. Someone said my PowerPoints were sad. They're just like sad and blue. And I'm like, yeah, I can see that, right? In the midst of those things. Some people said class wasn't very hard. Some people said class was way harder than they thought. And so there's a little bit of difficulty in trying to wade through things. But some of the consistent things, okay, like I said, was you guys would like, we may do more actual, rather than in-class things, take things home, work on it, bring it back, and then spend 10 minutes and try to get a little more time for doing things in class. Assignments like that. We're going to try taking the quizzes at the end, okay? At the end of the lecture material, at the end of class, not at the start. It seemed to be that it was stressing a bunch of you out, which was not my intent. I was thinking this is easy, easy grades. I'm going to do this other stuff. So we're going to try it at the end, okay? So you guys will note that I've already put the metabolism quiz up. It will be at the end of class next Monday, okay? That was the other thing that you guys said about Canvas is hey, can we put some dates and things in there so y'all can try to plan better? That's not a problem. Some of the quiz things it's hard because I'm not always 100% sure when we're going to be able to do things, so we'll work on it. So we're going to move you to the end. Okay. Same thing though. Fill out your lecture outline, and we'll go over stuff. You can supplement your lecture outline. You can try to use it on the quiz. So we'll try that for the next test, and we'll see how we do. Okay. With those things, and then I'm going back and doing it for this, and I'm gonna have to go back and do it for metabolism. But there was also you guys asked for if I could put some more stuff on the slides to remind you guys about what the graphs are. And so I'm gonna start adding a few things in the notes section on the PowerPoints. Be like, hey, this graph on the left is this. This graph on the right is this. Remember, here's why it was important. So that when you're having to go back, if you haven't written things down, that's not a problem. I've done this enough. I know what I want to say, but I can also very much appreciate how that can be a little bit of a problem if you guys are trying to write stuff down. So I'll do a little bit of that. So at some point, and I'll let you guys know when, I'm going to pull down this PowerPoint and I'll reload it with those in the notes. And I'll let you guys know when I do it. And I'll look at the metabolism one. The next few lectures, there's going to be less things like this and more, it's going to look more like probably what you guys did in human physical. Here's the signaling pathway. There's going to be a little less data, a little more just kind of cartoons and things. But we'll work with all of that. Okay? And we'll see about some fair answer possible questions soon. That was the other thing everybody wanted. It was like, those were great. Could we get them sooner? And I've not really decided. Because there was a part of it that really wants you all to study and look at things. And not just study what those questions are going to be. But I know I appreciate where you're coming from. So I'm trying to think about some clever things for that. Okay. All right. We're good? Yes? Okay. So again, remember I told you guys this woman, her name is Sue Bodine. She was at OMRF in Oklahoma City. Now But this is one of the very, very first studies. And all that I'm showing you guys don't have to kind of rethinking if I should even do this, but what we see here is if we apply rapamycin to a muscle. You guys remember last time, from a cellular standpoint, the thing that matters the most is activating this molecule called mTOR. If you want to hypertrophy your muscles, we need to activate mTOR. Okay? And so the reason that we know that is because in 2001, Sue published this paper. And they did a 7 or 14-day animal model of what they're going to call compensatory hypertrophy. When you lift weights, that's called compensatory hypertrophy. Your muscles get bigger. It's compensating for the extra load. But they have, right? In this one, there's no controls, but they have compensatory hypertrophy model here at 7 days, and then the same thing plus giving those muscles, those animals, rapamycin, which is the antibiotic that blocks the function of mTOR. So we get very, very blunted hypertrophy at 14 days. Again, very, very blunted hypertrophy. Okay. Similarly, you guys may think, like, why in some ways is this important? Well, they also looked at it by fiber type. Okay. We did not know 25 years ago if rapamycin was the primary signaling thing, or mTOR is the primary signal in both fast and slow twitch fibers. There was some evidence that maybe fast twitch fibers will hypertrophy more than slow, and so maybe they have more mTOR, right? Or maybe slow twitch fibers have less mTOR. Something like all of that. And what she showed basically was, here's a control. Animals they waited 14 days and they excised the muscle, right? Nothing really happens. This is how big it was. Here's compensatory hypertrophy in the white, right? So we're getting almost a doubling in muscle size. And then here it is with the rapamycin, basically very, very blunted, really no change in control. Very similar things in slow twitch fibers. And so this is how we began to paint the picture that mTOR is important. Okay, we need to activate mTOR to get muscle hypertrophy. And there seems to be a relatively similar amount and a similar signaling process in both fast and slow twitch fibers, okay, to generate compensatory hypertrophy. Okay. So in that way, if there is a genetic difference in the potential of 2s and 1s to hypertrophy, it's likely not due to differences in mTOR. Right? Questions about that? All I want you guys to know is that the primary cellular thing that drives hypertrophy is mTOR. Okay? When we do squats, when we load our muscles, when we stretch our muscles, we do things, what we're trying to do is to get something to activate mTOR. And that then tells the nucleus to make protein. Okay. So you may now ask, all right, well, Dr. Black, that's great. We know we have to activate mTOR to get all of these downstream things that are going to go on to drive protein synthesis, but what is it that's so unique about exercise? What is it that's so unique about resistance training, right? Because if I say you got to contract your muscles, we go for a run, right? Lots of muscle contractions when you run. You run downhill, you get lots of eccentric contractions and stretching. If you sprint, you may generate just as much force as you do when you're doing squats and those kinds. They can be very, very high force. And yet you would never go for a run and think that's going to make your muscles. So you're going to ask Dr. Black, what goes on? And the question and the answer really is, we still don't know. Okay? This is a diagram from a guy who's in the lab at the University of Wisconsin. And what he's going to say is there's this mechanoreceptor. There's this sort of unnamed, unknown ability of the muscles to sense high forces that disrupt the membrane, that disrupt the sarcolemma as you load the muscle. And there's something about the combination of that with the hormone release that we do get during a bout of exercise, as long as you're getting some testosterone, some growth hormones, some insulin, also in combination with eating some protein and maybe some carbohydrates, so that we've got stuff available. There's some kind of Goldilocks zone of all of these things together that are going to let us get hypertrophy. But we don't know for sure. Okay? We still don't know for sure. We can, in animal models, some things work, don't necessarily work in humans, and so we're still trying to figure all of this out. Okay? We're still trying to figure it out. But I just want you guys to kind of be just generally aware of that. And here's the myostatin that my group mentioned. Okay. This is what's called a Belgian blue bull. Okay. I don't know, anybody go to the state fair a couple weeks ago? No, nobody's going. You all went. I don't know, they might have had a Belgian bull there. I'm not sure. They have all kinds of animals and those things, but this bull does not make myostatin. Okay. My dude has never lifted a weight in his life, and yet he's just walking around being real jacked. Okay. And so, because he lacks myostatin. And so the function of myostatin is to put a top end limit on how big can those fibers get. Okay. And when you don't have myostatin, it's much easier for them to be able to hypertrophy. And they will hypertrophy much more doing kind of relatively normal daily activities. That way. It functions by blocking satellite cells. Okay. So we know, right? I'm sorry, it partially blocks. Myostatin partially blocks the function of satellite cells. So if you've got a bunch of myostatin, satellite cells don't work very well. So it's hard for us to get growth and repair, or it's harder for us to get growth and repair. There are people, as I said, I don't know, you guys may not, many of you, maybe you have younger brothers and sisters or a kid of your own or things, but a 7-month-old is not supposed to have a visible vas lateralis. They're just like little balls of chub, right? Like little Michelin tire babies. They're great, but they don't have a lot of muscle in those ways. And so we've got a 7-month-old who is essentially myostatin deficient, and they have like 7-month-old babies have like muscle, which is kind of crazy. If you want to look at this, there's basically every animal on the planet where you can find some that are myostatin deficient. So you can Google myostatin deficient, like mice, rats, dogs, if you want, and they all look like a freaking bull, in those ways. Right?
Is this cause any sort of health issues in the future? People who are myostatin deficient?
Not that I am aware of. So we know that there is some evidence in people that are heavy resistance trainers that you may have elevated blood pressure responses and some things, and you may be at a slight increased risk for certain kinds of cardiovascular disease. But a lot of that is probably driven by something to do with the resistance training. It's not necessarily due to just having more muscle per se. I am not aware that there is anything. That's a great question. From that standpoint. And just because you don't have any myostatin, there's still a genetic limit. You're still only going to be so big. Okay. It's not like you're just going to be able to grow exponentially. But it may be one of those things if you guys sort of look around. You're like, yeah, my roommate doesn't really work out a lot, but they're real swole, right? Just kind of naturally. Maybe they have sort of lower levels of myostatin. See some expressions on faces if y'all found the dogs or the mice, right? Or like Doberman Pinscher looking dogs, it's just like this. Or they have the little mice, and like one mouse is like twice as big as the other little mouse, and those kinds of things. So it's really kind of a fascinating deal. So one of the things that contributes to that host of genetic variation that we mess up. Okay? All right. So I think that's the last slide. Oh, no. Okay. Cool. It's not. So we did this a little bit at the start, okay? And now I want to bring it back at the end and kind of revisit this. Remember, people typically resistance train because they want to get bigger muscles, they want to get stronger muscles, or they would like to do better in some sort of like performance, be that walking, running, jumping, sports, something like that. Okay. We know they get stronger, right? Somewhere between maybe 50 and 100%. That's mostly driven by changes in recruitment, right? Neural activation, and then some level of hypertrophy. Most of you guys can hypertrophy, maybe a little bit less than your increase in strength, so like maybe 10 to 25 or 30%. And that's mostly driven by activating mTOR, driving protein synthesis, and getting bigger muscle. Okay, so there's 2 minutes on 4 days of lecture, right there. Okay. Let's look and answer the big picture question that I asked on the very first day that we did this. Okay, which is you're going to work out today. We know that doing something is going to work, but what should you do today, right? Or I paid this person to tell me what to do. Is what they told me actually any better or worse than someone else? Okay. So what do we know about this? That's going to be kind of the last thing that we talk about here. Is what should we actually do? Okay. We know that there's lots of signals and things that contribute to hypertrophy. We know in some ways, okay, this is just for bigger muscle. We know that potentially peak muscular force or the load you lift may matter. It may matter. We know that total volume may matter. Okay, so how many reps, how many sets, how much weight are you lifting? Okay, that may matter. We definitely know that the contraction type matters. Doing con X, so up and down, right? Or if it's a squat, down and up was also the universal thing. Y'all are like, more squats, Dr. Black. So, I don't know if y'all are telling me I need to do some more myself because I've been getting a little sloppy down here, or just y'all like moving around, okay? Contraction type matters. The hormonal, I'm going to call it milieu, right? You need some hormones, okay? You need some. If you don't make any, or you're a woman going through menopause, or you're a man going through andropause, or you're my daughter who is prepubescent, they don't have any, they're not going to get big. Muscles are not going to change. So as long as we're in that kind of normal range, we need some hormone response. There has been this thought of is there metabolic demand. We're going to talk about next when we do metabolism. I have this on here, and there was a paper that came out like 2 weeks ago. It's now suggested that maybe metabolic demand is not a thing. Okay, it's a consequence of what we're doing with the metabolic side of things doesn't really matter. Okay, most studies that we know on things try to isolate one of these things compared to everything else. Okay, I'm going to leave all of my set numbers the same, and we're going to test if we change how many reps. Or I'm going to leave the sets and the reps the same, and we're going to change how much weight we lift. Or something along those lines. We're going to do all of that, and we're going to compare concentric to eccentric. And so there's literally hundreds of thousands of research papers on trying to understand the optimum resistance training regime. And we're inducing hypertrophy and we're inducing changes. What I want you guys to take away are 2 things. Very simple. Okay, 2 things. Okay, maybe 3. 2 things. 1, if you don't lift weights, or you haven't been lifting weights, okay? 1 set, 10 reps to failure. You guys know what failure is in relation to this? I'm going to do squats until I cannot do squats anymore. Okay? You cannot do 1 more rep. 1 set, 10 reps to failure, 1 day a week. In completely untrained people, works for about 6 to 8 weeks. You're going to get bigger muscles, you're going to get stronger. It does not take much if you do nothing. Okay? As you become more trained, we need to increase probably load and volume a little bit. So maybe we need 2 days a week. Rather than 1 set, we need 2 sets. Or rather than 2 sets, we need 3 sets. Okay? If we want hypertrophy, you want your muscles to be bigger, here's the thing you need to do. It's very, very simple. You need to resist them. Like 85% of the contribution to hypertrophy is just simply you need to go a couple of times a week, lift weights consistently for several months. That's the biggest thing. I did 3 sets, I did 2 sets, I did 8 reps, I did 6 reps, I did 12 reps. Man, we're really working in the margins on all of them. Okay? You need to go, you need to be consistent. 2 days per week is probably fine for a muscle group. And the other big thing that we know, how much weight you lift doesn't really matter very much. What matters is that you lift that weight until you can't do it anymore. Okay? You need to lift to failure. That's the big thing. Okay? Lift to failure. You're doing 3 sets of 15. As long as you can't do 16 reps, great. You're going to get roughly equal response from hypertrophy as if you were doing 3 sets of 4. And in your sets of 4, you couldn't do a 5th rep. Okay? That's a relatively recent development in exercise physiology. We used to think it needed to be heavier weights. Okay? But you can lift a lighter weight. You can do push-ups with your body weight and get hypertrophy as long as you're doing push-ups until you can't do anything. Okay? That's the key thing. But that's hard for most people. If you're doing a lighter weight, it's hard. Like, I gotta do like 25 reps, you want to stop before you get there. Sometimes that's a little easier to do if you're doing 3 or 4 or 6 reps. Okay? Going to failure is the thing that seems to matter. Failure gets you hypertrophy. If you want to increase strength, this is where the amount of weight you lift really matters. If you want to get and maximize how strong you're going to get, you have to lift heavy weights. You're going to adapt to the nervous system to whatever stress you put on it. So if you want your 1 rep max to go up, okay, you have to lift heavy. Sort of hard to take. Failure gets you hypertrophy. Heavy weights gets you bigger increase in strength. Okay. One of our former graduate students, he essentially took my position at Ole Miss. And they have a bunch of research from his lab where all they do is have people come in and they max out 3 times a week. Come in and do your 1 rep max 3 times a week. They get greater increases in strength from doing that than people that come in 3 times a week and do 3 sets of 5 with 85% of 1 rep max, or whatever kind of a more traditional thing is. Because you're testing them, right? Max strength is the test. And so all you're doing is practicing the test. You get better through the test. We think about this when we do sports all the time. You want to get better at shooting free throws, you got to shoot free throws, right? Practice what the actual test is going to be. Okay? The adaptations are going to be there. So that's what I would say. Anybody that tries to tell you need to do 14 sets of 2 or whatever it is, they're trying to sell you something. Go 2 times per week, do 3 sets of 6 or 2 sets between 6 and 12 reps, 2 or 3 sets, a couple of times per week, work to failure. When it gets where you can do all of those reps and do a couple of extra ones, make it heavier again. You're better off than 95% of all people that do exercise training. The rest of it is all fluff. It's all bullshit. It's all, I'm a personal trainer and I want to sell you one thing. To me, the real value of personal training and coaching and those kinds of things is one-to-one. It's behavior. I'm paying for you to train me, so I'm going to show up. You're here, so I'm going to work harder and I'm going to do more reps. I'm going to get to failure easier because you're here. Okay. And then maybe you're going to give me a little bit of other stuff, or I can do a lift that I couldn't do otherwise because you're here to spot me in those things. Okay. There's real value in coaching and training and all of these things, but it's not necessarily, the value is not in, well, I have some secret thing. We're going to do TheraBand while sitting on a Bosu ball and with one eye closed, doing this kind of thing, right? Right? That's kind of what it is. And it's not that. That's the little thing. All right. Questions? So what are we going to do today? Wednesday, we're gonna lift today? Good. Yeah? Okay. Good deal. I need y'all to hold me to it. Right? Tomorrow, I'm not sure if I will be here. Tomorrow at 2, we over at the hop. We'll go, I don't know. We'll go do old man legs. Okay, whatever that's gonna look like.
Okay, so very good.
Let's sit down on this. So the next thing that we're going to talk about is metabolism. I'm sitting down because I need to be able to duck. This is probably the most conceptually difficult thing that you guys would do in our major. Okay? It's metabolism. A lot of that is not y'all's fault. Okay, metabolism is hard, and y'all probably been, the way it's been presented and taught to you in previous classes is technically accurate, but leaves out some of the big picture of how things work together. And I find that that makes it a little bit trickier for you guys, because what I'm going to show you all is a little bit different than how you've learned it before. Okay, a little bit different. And so I think that's why it's going to be a little conceptually difficult. So I will try to keep the big picture in mind, and I will try to point out the places where I think people are going to get a little bit tripped up. Okay, or people are going to get tripped up. We'll also tell you all that you're not going to have to memorize these pathways. Okay, I'll show you what I want you to know. This is not going to be Dr. Mike would make everybody, when he taught XPhys, you had to memorize all the steps in glycolysis, all the steps in the Krebs cycle, and those things. If anybody had biochemistry? No? Okay. You got to memorize them, and you got to know the molecular, the sort of organic structure of all of the different things and the enzymes and everything else. It's pretty gross. Okay. Mostly what I want you guys to know is what goes in and what comes out. Okay. What goes in and what comes out. And then some key things that control it. Okay. All right. So the idea of metabolism. And I hope once I say this, you all will understand why we've already spent a bunch of time doing some of the things that we've done. Okay? So, I am moving. How do I move? What do I have to do to be able to move? Hey, do I have to move? Good. Okay. I have to contract my muscle. So that my muscles will generate what that lets me move? Move. Yes, force. Good. Okay. Like this. It's good, right? Big picture. I am walking. Okay. Now, would you guys say, be lawyer, would you stipulate that as I am walking, if the idea of metabolism is energy, okay, am I using more energy? Is my metabolism elevated as I walk in comparison to just standing? Am I burning more calories? That's what metabolism is, calories, burning calories. Am I burning more energy? Does it cost me more energy to walk than standing? Okay. What's different between walking and standing? Okay, I'm moving. Good. And when I move, what do I have to generate to let me move? Force. Where does the force come from? It comes from muscles. Where in the muscle? Cross-bridge sucker. Okay? Everything comes back to the stupid cross-bridge sucker. Right? You guys haven't figured that out now. I am walking. Why is my metabolism elevated? Because I'm breaking a bunch of cross bridges. I'm repolarizing and running the sodium potassium pump. I'm repolarizing neurons in the sarcolemma. I'm using energy in the calcium ATPase or in circa to pull calcium back into the sarcoplasmic reticulum. All of that costs me energy. Okay? So when I'm walking, the reason my metabolism is elevated is because of force sharing. It's all about the cross-bridge cycle and that signal. There's more of that that's going on than before. Okay? So that's why we do that first. I want you all to understand this is where the increased ATP use is coming from inside of your cells. So if I'm walking and it's up a little bit, what happens? This will be fun. I start jogging. Is it up more? Yes. Okay. Why is it up more? Yes. Why do I have to break them faster? I think somebody's got it. We're a little mumbling, but that's okay. Everybody wants to say it, right? Force velocity curve. I gotta go faster, so I gotta break more. And, right, as I break more, I get less force, so I gotta recruit more muscle to get whatever force I need to go that fast. So, more cross-bridge cycling, I need more force to go that way. Okay? And the faster that I do it, then I have to repolarize more and faster. I have to pull the calcium back in more, not faster, but more. So I'm using more energy. Okay? So, does that part make sense? This is why physical activity, this is why exercising raises your metabolism. Okay? If we can keep those things in mind as we work our way through all of this, we're going to be in good shape. Okay? We're going to be in good shape. All right. Now, what you see here is a very, very kind of brief summary of things. Okay? We are going to talk about multiple metabolic pathways. And a metabolic pathway has one real goal. Its goal is make ATP, right? I'm standing, I need a certain amount of ATP. I'm walking, I need more ATP. I got to get it from somewhere, right? I'm jogging, I need even more still. I got to get it from somewhere. So what we're going to use are multiple metabolic pathways that will break down what we call metabolic substrates. Okay? A substrate is the thing that goes into the pathway and gets broken down that allows us then to make ATP. Okay, so we will talk about some anaerobic pathways, things that don't use oxygen. We'll talk about aerobic pathways, ones that do use oxygen. Okay, and kind of the push and pull of those two things with each other. We'll talk about how and which pathways use carbohydrate. We'll talk about which pathways could use protein. Most of they don't. And then which pathways. Okay. Then we'll try to contextualize why in some circumstances will we use one pathway over another, and why in some circumstances might we use carbohydrate instead of fat, or fat instead of carbohydrate. Okay? And that's what I want you guys to try to get out of all of this. Who is like me and has not had breakfast? Okay? All of us are getting more energy just sitting here from fat than those of you that had breakfast this morning. Okay? And there's a reason, and we'll explain why that's going to be the case. Okay? If I ask someone to stand up and start doing some squats, immediately you're going to use a pathway called the creatine phosphate pathway to get energy to do those squats for about 10 seconds. There's a reason that's what we have to use, and we're not going to use a different one. So we will try to talk about the pathways. What are they? Okay, how do they work? What are their control points? Why are some fast and some slow? But then we're going to put them all together and try to understand, okay, as I'm walking, I need more ATP, but what am I getting? Where am I getting it from? What pathway is going to give it to me? What substrate is it going to use? And then how might that change if I go from walking to running, or how might it change if I go from walking for 10 seconds to walking for an hour? Because those things are going to change. Okay. So far, so good. All right. We're going to keep coming back to that.
Okay.
So, really, really, really important kind of things. And there are people that will say that metabolism is the most important thing in exercise physiology. Okay. Anybody remember what it was that A.V. Hill won a Nobel Prize for? Metabolism, right? Okay. We're still basically studying the exact same thing that he was 100 years ago to try to understand muscle metabolism. Okay. It's very important. Why is metabolism so important? It's because we have to move. Okay. And we have to have energy for your heart, your diaphragm, so that you can breathe and move your lungs. And we have to have energy for your brain. So without metabolism, we die. We can't move. It's kind of least of our problems. But we have to have it to be able to move and to do things and to run our other bodily functions. Okay. In the context of exercise, the change in metabolism is mostly going to track the change in force production at the muscle. Okay? But it's the change in metabolism rather than the force production. So it's the change in energy use that mostly drives the other physiological responses that we see during exercise. Okay? Who remembers? Taylor, do you remember what happens to heart rate as I start going from walking to jogging? Heart rate increases. Good. It's cardiac output goes up. Why does heart rate and cardiac output have to go up? Well, we need more oxygen because metabolism has gone up. Okay? Why does breathing rate go up during exercise? We need more oxygen, right? Why does blood go to my muscles? Well, because that's where the metabolism is. So the vast majority of the physiological changes in the cardiorespiratory system, okay, are going to be in response to where and to what extent we need more ATP in our muscles to let us exercise. So it's really, really important. Changes in metabolism drive hormone changes as well. Because a lot of the hormone changes, things that change during exercise. Epinephrine, norepinephrine, cortisol, growth hormone, insulin, glucagon. All of these things change during exercise. But they mostly change to try to provide us carbohydrate or fat to stick into metabolic pathways. Right? So they're mostly going to be the result of changes in metabolism. Very often, especially for aerobic metabolic training adaptations are very often proportional to energy use during exercise and the metabolic systems that were taxed during that bout of exercise. Okay? Finally, if you're an athlete, or maybe you're not an athlete per se, but you're a person that you want to run a marathon or run a half marathon, or run a 5K, or carry your toddler around on your back, whatever it is, get up and down stairs. In a lot of instances, movement or physical performance is going to be limited by your ability to supply additional energy to your muscles. Okay? So if I had somebody get up and do push-ups right now, anybody want to volunteer to do push-ups? No volunteers. This is where it can be real fun. Like, Montana, pick somebody, we're going to do push-ups. Great, then I guess you're going to do push-ups. I'm kidding. So, if we had Montana do push-ups until she couldn't do them anymore, the primary reason that she stops doing the push-ups is because she's run out of her ability to provide enough ATP to the muscles to meet that metabolic demand. That is going to be the consequence of however much force she needs to do those push-ups. She can do them to start with, right? But at some point she stops having enough ATP. She can't break her cross bridges, she can't repolarize, she can't resequester calcium, and so she will very likely. Okay. So in this particular context, metabolism is wildly important. Okay, it's wildly important. And that's why we're going to spend quite a bit of time. Okay. There's one person that's had biopsy. We've all had like Kim Warren, right? Like Jim Kim, something, yes? I should know the answer to that. I'm pretty sure. Okay. So you guys may talk about that in chemistry. I don't remember exactly where the first time that I learned about this. Okay. But the concept of bioenergetics, right, is what we're going to get at in metabolism. Okay. The concept of that there's this exchange and flow of energy within living systems. Okay. One of the first law of thermodynamics. You can't create or destroy energy, we just move it from one place to another or from one molecule to another. Okay? And that's what's really true with metabolism in our bodies, metabolism, muscle metabolism, okay, that helps us to exercise. All of you have in your muscle fiber some ATP. Okay? You have some ATP. The problem is you have a tiny amount. Why might you only have a tiny amount of ATP in your muscles?
Because there's a limited amount of resources to make ATP.
Okay, okay. You're close, Jasmine. You're close. What else? What else is in your muscle?
Powerhouse.
Powerhouse? What is the powerhouse? Mitochondria is short for what? Mitochondria. There are mitochondria in your muscles, yes. What else is in your muscle? Calcium, sure, where's the calcium? Plasma reticulum. Muscles are mostly water and protein. What are those proteins? Right, we put them all together, but what's protein we're making? Sorry. Actin, myosin, right? So to take home, there's a bunch of other shit in your muscle. There's not space for ATP. Okay? The amount of ATP that you use that I use to walk across the stage is more ATP than you could fit basically in like my entire quad muscle. Okay? And yet I can walk and it's not a problem. So, and I say all of this to illustrate this concept. This will be the last thing that we do today. Okay? You have a very small amount of ATP in any tissue in your body. Okay? And this is why metabolism is so important. Because what we are doing is, I take a step, all that ATP that was stored in my muscle is gone. I've used all of it. Okay? And yet I'm able to go step, 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 okay? And the reason that I can do that is going to get into this flow and exchange of energy. We have ATP, we break it down, and then we have a capacity through our metabolic path to immediately remake that ATP. Okay? And then continue to do that over and over and over. So what you really have in your muscles, think about it this way. You have, guess remember what's the A in ATP stand for? It's adenosine. Think of it as you have these adenosine like scaffolds that are there. Okay? And you have X amount of adenosine that's in your muscle. And all that we're doing is the adenosine just gets sort of shuttled around. And it's like Ubers, right? There's a certain number of Ubers that are driving around. So, right, hopefully it'll become pertinent for you guys in the next few days in Dallas if you go. There's Ubers, there's a certain number of Ubers, and all we're doing is somebody gets in the Uber, that's a phosphate. You go someplace, somebody gets out, we've broken down that ATP, then the Uber just loops back around, picks up somebody else, takes them over here, drops them off, comes back around, picks them up, drops them off, picks them up, drops them off. That's what happens with metabolism. Okay? You have ATP, any amount of force generation, you blow through all of that ATP, and then we use our metabolic pathways to immediately start putting phosphates back onto ADP to make ATP again. Then it gets broken down again almost immediately. Then we resynthesize again almost immediately. And so there's just this constant cycling, okay, of breakdown, build up, breakdown, build up. And as long as you can continue to build it back up to a level that is sufficient to allow you whatever force production you need, then you're going to be okay. But at some point you can't. All right. So we're going to do that. All right. Test return by Friday. Enjoy your day or 3 days off, whatever it's going to be. Please make the choices that don't want to see on the news. Okay. If you did not turn in your start of class assignment, please make sure that you do. All right. All right.